Edexcel Further Maths, Core Pure 1, Specimen Paper, Question 6. When we first look at a question like this, we want to skim through and get a sense of what the topic might be. At the very end, it talks about plotting roots on an Argand diagram, so we know that something to do with complex numbers is involved. And then as we read through, we can see it talks about the imaginary axis as well in the second bullet point. But at the very beginning, it's essentially defined for us two functions. One of them is a quadratic, and one of them is a cubic. We know that because k and m are constants, so they have nothing to do with x. They don't vary as x varies. But this means that we only have limited information about these two functions, because unless we know the constants, it's hard to say what the roots would be. We can't say exactly what the roots would be, and potentially, depending on the constants that are missing, maybe there are no roots, or maybe there are only certain roots possible. That's why they're giving us some extra clues, and it's up to us to make use of their clues in the two bullet points to deduce the various other bits of information about them. Specifically, we want to solve completely f of x equals 0 and g of x equals 0, which means we're looking for all of the roots of the quadratic and the cubic, which means that this question involves roots of polynomials. We have a few results involving roots of polynomials that we can use, and I'd encourage you to remember here there are various approaches you can take here. But generally speaking, it's worth being familiar with and fluent with the various different approaches, because sometimes one of them will be much quicker and more efficient than another one. Let's start with the first bullet point and see if we can write down anything in equation form from what they've told us. The sum of the roots of f is equal to the product of the roots of g. So let's start with the sum of the roots of f. What does that mean? Well, the notation we tend to use is a capital sigma and then alpha to represent the sum of the roots. Now, if it's a quadratic, that's just the same as alpha plus beta, but if it was a cubic, it'd be alpha plus beta plus gamma. This is shorthand for the sum of the roots, and we should know from Vieti's formulae that that's the same as minus b over a. In fact, for a question like this, it's not a bad idea to jot these results down, at least the first few, to remind yourself how they work and so that you can refer to them without getting confused later on in the question. The sum of the pairs of the roots, which is normally abbreviated as the sum of alpha beta. So in the case of a quadratic, that's literally just alpha beta, but for a cubic, it'd be alpha beta plus alpha gamma plus beta gamma. That's equal to positive c over a. And if we go as far as the sum of the triplets, we call it alpha beta gamma, and that's negative d over a. We can go further, but the pattern continues, so that's normally enough. You can refer to that to get your signs correct as we go along. So the sum of the roots of f can be calculated by doing minus b over a, which in this case is minus 3 over k. I'm not too concerned that I haven't got a value for this yet, because this is just one of a number of clues that I can make use of. I've got the sum of the roots of f. Now I'm going to get the product of the roots of g. And the product of the roots is actually this one, because the product of the roots when you've only got three roots is the same as the sum of all triplets of the roots. So minus d over a is minus 9 over m. So 9 over m. Therefore, I've got an equation I can write down straight away. Minus 3 over k equals 9 over m. Well, equivalently, if I want to write it a bit more nicely, I've got minus 3m equals 9k. You can even divide both sides by 3 and get minus m equals 3k. Or maybe m equals minus 3k, something like that. We've got a nice, easy equation. We could substitute for m or for k. K equals minus a third of m. Later on, once we find another link between m and k. So this is a good start. There were two unknowns, and once we found them both, we can solve f of x equals 0, g of x equals 0. The first bit of information we were given gave us one link between them. I'm hoping the second bit will give us enough information to find another link between them. G has at least one root on the imaginary axis. This feels like less information than you need. It's not telling you the size of the root. It's not telling you if there are any other roots on the imaginary axis. But if you remember what we know about cubics always have at least one real solution. Think about a cubic graph. It must cross the x-axis somewhere. which means that the other solutions don't have to be necessarily real, even if the coefficients are all real, which in this case they are. It says K and M are real constants. So if we have a complex number as one of our roots, we're going to need another complex number for the other root, that is the complex conjugate. It's one of these results about cubics that you can look into and refresh your memory with if you need to. If you've got one complex root, there will be another root which is also complex and is the complex conjugate of your first root. So let's give a name to this root on the imaginary axis. Let's say let alpha equal pi. So p is a real number, I is the imaginary unit. If it's on the imaginary axis, it means it has no real component and just an imaginary component. So we'll have the imaginary component as being p times I. Then, since the cubic has real coefficients, the conjugate is also a root. So we'll say beta is equal to, now the complex conjugate of pi is minus pi. Because you keep the real bit the same, in this case that's 0, and you change the sign of the imaginary bit. Alternatively, think of it as reflecting in the real line, or changing the argument to the negative, so instead of a 90-degree argument, it's a minus 90-degree argument. Now we have alpha and beta. We've got two of the roots in a sense. They're kind of in relation to one another. But how are we going to make use of that idea? Well, there's a few options. And the options all come from the additional information that is hidden inside these. So let's focus on the cubic, because that's the bit we've just been given more information about. We've got the x squared coefficient, we've got the x coefficient. We've made use of the constant already, so I'm not going to come back to that just yet, but that was where we got our 9 over m from. What I'm interested in now is one of these two, but also possibly the m, because I'm trying to find a link between m and k. So if you don't know what else to try, then just jot down the things that you know and substitute things in and construct yourself a few formulae. You might find there's some more efficient ways of doing things as you get more familiar with this. I'm going to jot these down and see what each of them give me now that I've got some more information about the roots, alpha and beta. The last one is some real root. The final root, gamma, is some real number. I don't know what it is, so I'll leave it as gamma for now. But we know that the sum of the roots, minus b over a, the sum of the roots has got to be pi plus minus pi plus gamma. So that's just gamma, because the two complex conjugate roots cancel out entirely in this particular case because their real component is 0. We also know that that's equal to minus b over a, where b is minus 2 and a is m. So it's minus 2 over m. So we get 2 over m. Now we've got a direct link between that third root and m. So that's helpful. Let's see what we get from these other two results. The sum of the pairs. Now this may seem a bit tedious. You've got to go through all three different pairings, but some of them are quite quick and easy. For instance, alpha beta itself is pi times minus pi. That's minus p squared I squared. But I squared is negative 1 by the definition of I. So minus p squared times minus 1 is just p squared. What about alpha times gamma? Well, here's where I'm going to save myself a bit of time as well. Pi gamma, and then minus pi gamma. Alpha times gamma and beta times gamma added together, they're going to cancel out because alpha and beta are the reciprocal, are the negatives of one number, not just the conjugates, but the negatives in this particular case. So we got p squared. And what about the other side of this, the c over a? Well, c is 3, so 3 over m. Now I've got a link between gamma and p indirectly via m. And also for completeness, we're going to do this last one. The product. Well, for this, I've already got alpha times beta because I worked that out when I did the sum of the pairs. That was just p squared minus p squared I squared. That's p squared. and I just need p squared multiplied by gamma. And of course, minus d over a we worked out before, but we can do it again. Minus 9 over m. 9 over m. So how is this going to help us? Well, having written them all out like this, I can see one way straight away that might be useful. I've got p squared, I've got gamma, and I've got p squared gamma. But this is not just a restatement of these two. If I multiply the first and the second equations together effectively, or I multiply their left-hand sides, I multiply their right-hand sides, I should be able to find m. I can say that 3 over m, which is p squared, times 2 over m, which is gamma, is equal to 9 over m. And that gives me 6 over m squared equals 9 over m, or 2m equals 3m squared. I've multiplied both sides by m squared and divided both sides by 3. Now, from here, I can find m as 2/3 if I divide by m and by 3. The only question you've got to be asking yourself is, what about m equals 0? That's a possibility, right? Well, if we go up here, it says it's a real constant. If m were 0, that wouldn't necessarily contradict this statement, but if we come back and look at some of these, we'll find that one of our roots will be 2 over m, which can't work if m is 0. So we can safely say here, m is not equal to 0. Therefore, m is equal to 2/3. Now we've got 2/3, a lot of other things will start falling into place. For instance, m is equal to minus 3k. So we can say k is minus 1/3 of m, which is minus 2 over 9. Now we've got k. We can find the roots of f straight away. You might have noticed, because f is a quadratic, it's going to be a nice, easy one to solve. Minus 2/9 of x squared, because it was kx squared, plus 3x minus 11. So if we want to solve this, f of x equals 0, it's equivalent to solving this little quadratic, which we don't need to do by hand. Just because we've done a lot of the other stuff directly and in a sophisticated mathematical way, doesn't mean we're not entitled to use the calculator for this bit. Minus 2 over 9, 3 minus 11. The mark scheme explicitly says that it's fine to use the calculator for this. And in general, that is the case. You're going to be given a maximum of 1 mark for work like this, so don't anticipate spending ages and ages or writing out the quadratic formula. It's not wrong, but it's not the most efficient way. 27 plus 3 root 7i over 4 and 27 minus 3 root 7i over 4. So we've got two solutions here for the roots of f. That was the first part of the question that was asked. They said solve completely f of x equals 0, but also g of x equals 0. That's the cubic. We're going to need to do that one as well. To solve the cubic, we're going to need to go back and use our value for m. But remember, we've already got this, which is going to help us. Gamma equals 2 over m. So roots of g can be found from this. Gamma equals 2 over m. M is 2/3, so it's 2 over 2/3, which is a little bit of an awkward thing to write. Be careful if you're writing fractions within fractions. My favourite trick here is to multiply top and bottom by whichever awkward denominator is causing you problems. But you might be able to see already that if you do 2 divided by 2 divided by 3, you get back to 3. So we've got the real root. There was also, up here, a link between p squared and m. So I'm going to use that one as well. There are various other roots through that we can go for here. But this is going to be 3 over 2/3, which is the same as 9 over 2. So we've got p squared. That will allow me to find p, plus or minus 3 over root 2. Or you might prefer to write it as 3 root 2 over 2. Plus or minus doesn't need to cause us any concern here. what we're saying is one of the roots is 3 root 2 over 2i, and the other thing it could have been is minus 3 root 2 over 2i. But we know that the second of those two complex conjugate roots is just the negative of the first. So both of those are valid. Depending on which one we pick for p, we'll have the other one for the negative p. So without loss of generality, that means we're not losing any solutions by saying this. We're going to say let p equal 3 root 2 over 2. Therefore, the roots of g are 3 root 2 over 2i minus 3 root 2 over 2i and 3. Number 3. It's worth remembering that now you've got the value of m, we can, what is it, m is 2/3, we can check. In the same way that we solved the quadratic, you could solve the cubic on the calculator. So we're solving 2/3 x cubed minus 2x squared plus 3x minus 9. So menu option A, polynomial degree 3, we can put in 2/3, minus 2, 3, and minus 9, and check that we get 3 for our real solution, this weird number, and its conjugate, 2.12 and minus 2.12. And then you could check back. Unfortunately, it's not easy to save this and refer back to it because this is within the polynomial solving mode. But if you take a good look at it or you jot it down, then that should be sufficient. All we need to do next is go to the normal mode and say 3 root 2 over 2 and check that what we're getting there looks like what we just got as a decimal. So 2.121 something. I'm happy with that. So the solutions given above are the ones the calculator gives, so I'm happy with those. Those are my solutions for the roots of g. And then if you're anything like me, you'll move on feeling smug that you've finished. But there's a whole second part. Part B, plot the roots on a single Argand diagram. So we need to put all of those on an Argand diagram. It's a quick 2-mark way of testing you on Argand diagrams, even though the bulk of the question was roots of polynomials. So we'll look back at our roots and we'll see how we can put them on the Argand diagram. Remember, the roots of that quadratic were in fact complex numbers themselves. It's a little bit messy to interpret in that current form, but not impossible. We can, to make it easier for us to plot these, I would recommend approximate versions of them. So obviously 27 over 4 is a fairly easy one to get an approximation for. We're looking at 6.75. That's not even an approximation, that's exact. But 3 root 7 over 4, that's going to be the size of the imaginary component, plus or minus 3 root 7 over 4. So we've got plus or minus about 1.98i. Now that gives me a good enough sense of the size of the number that I can plot it on the Argand diagram. Roots of f, g. So I've got 3, and just to remind myself, the other number 3 root 2 over 2 looks like 2.12. So I'm going to plot these 5 points on an Argand diagram. I'm going to show you how precise it needs to be and how precise it doesn't need to be with a quick graph. So you don't need to be particularly beautiful or even to be able to draw particularly beautifully to make this work. All you need is something roughly to scale. We need to go as far as 6.75 to the right, and we need to go as far up as 3 for that one, so that's all fine. We need to go up and down roughly 2 in the I direction. So let's say we make our Argand diagram like this. We mark on some approximate values, so 1 and 2 up there, minus 1 and minus 2. And roughly speaking, we'd have a 3 here, we'd have a 6 here, and then we mark on our points based on this. So 6.75 plus or minus about 2i. So we're going to have 1 point about here, 1 point down here. Those are the complex conjugate roots of the quadratic. Then we have 3, which is purely real, and we have plus or minus 2.12i. So that'll be just a little higher up than we've got here. A little lower down than we've got here. That should do. The only other thing I'd recommend, I'm not going to write them all on because it would take a little too long here, but I would recommend indicating on your sketch the precise values. So you've shown where they are or what they look like if they're drawn on an Argand diagram. If you've also got these written out next to it, that would be great. If you could write them directly next to each one, that's even clearer, so that it's obvious to the examiner which solutions correspond to what. And that is question 6.